All right, today we are diving deep into a high-stakes digital heist. It's a story about how a really powerful data tool completely transformed the fight against tax fraud, turning a super flawed system into a precision crime-fighting machine. So, let's just start with the big question on everyone's mind. How do you stop a multi-billion-dollar heist when the thieves are basically hiding in plain sight? We're not talking about a single bank vault here. This is about millions upon millions of digital transactions. And the criminals? They're not masked bandits. Nope. They're practically invisible, just using stolen identities to file fraudulent claims on an absolutely massive scale. And when I say massive scale, just look at this number. $5.8 billion. That's how much the IRS paid out in just 1 year on claims they only found out were fake after the money was gone. That's billions just lost, all because the system couldn't spot the lie in time. So to really see how you fight this kind of invisible crime, we need to zoom in on a real-world case. We're going to head to the state of Maryland, which was dealing with its own huge wave of fraudulent tax claims. Now, their problem wasn't a lack of effort, not at all. Their system was flagging a staggering 110,000 tax returns as suspicious every single year. But here's the real kicker: an incredible 90% of those flagged returns were totally legit. And this had a real human cost. Andy Schofel, who's the director of Maryland's Bureau of Revenue Estimates, he put it perfectly. He said the thought of holding up all those refunds was just tough to stomach. They were basically penalizing tens of thousands of innocent people who were really counting on that money. The system was catching way too many dolphins in its tuna net, if you know what I mean. Okay, so Maryland needed a new weapon, a better way. They turned to a technology that acts like a digital evidence locker, really. A way to store and analyze clues on a massive scale. And this weapon, it's called a data warehouse. So what exactly is a data warehouse? Well, think of it as a special kind of database that's built for just one thing: analysis. It pulls together all this current and historical data from all over an organization. And the keys here are that the data is integrated, which just means information from different places is all made to speak the same language, and time variant, which is a fancy way of saying it tracks changes over time. And that makes it perfect for spotting patterns. Now, it is absolutely crucial to understand this is not the same thing as the database that runs daily operations. Think of a regular transactional database, they call it OLTP, as a cashier's terminal at a grocery store. It's fast, it's efficient, and it handles one transaction at a time. A data warehouse, or OLAP, is the complete opposite. It's the investigator's evidence locker, and it's built for deep, complex analysis. And this chart really lays out the difference perfectly. The whole purpose of the transactional system, OLTP, is just to run the business day to day. But the analytical system, OLAP, that's all about supporting big-picture decision-making. One uses live data for simple, routine reports. The other uses historical data to answer complex, spontaneous questions. They're just two different tools for two very different jobs. Okay, so how do you get all of that messy, raw data into this pristine, analysis-ready evidence locker? Well, that's where a really critical three-step process comes in. It's all designed to build what they call a single source of truth. It's called ETL. That stands for Extract, Transform, and Load. You can think of this as the engine that takes data from all these different countless sources and gets it ready for investigation inside the data warehouse. So first up, you extract. This means data gets pulled from literally everywhere. We're talking old mainframe systems, modern software, simple spreadsheets, web logs, you name it. It's that first big step of just gathering all the potential clues, no matter what format they're in. Next up is transform. And honestly, this is the most important step. This is where the magic really happens. All that raw data gets cleansed of errors, it's standardized into one single format, and it gets organized. It's kind of like taking a bunch of messy, conflicting witness statements and organizing them all into one clear, consistent timeline. And finally, you load. The clean, reliable, and now transformed data is loaded into the data warehouse. At this point, the digital evidence locker is stocked, and it's ready for the analysts to come in and start connecting the dots. Okay, so let's get back to our Maryland case study. With their new data warehouse all set up and running, what happened? Well, the results were immediate and, frankly, pretty dramatic. Just remember this number, okay? The old system, it was only right 10% of the time. That means for every 10 returns it flagged, 9 of them were totally innocent.
Now, with the data warehouse, the new accuracy rate jumped to 65%. I mean, that is a monumental leap. They went from being wrong 90% of the time to being right most of the time.
I mean, this chart just says it all, doesn't it? Look at that jump. That's more than a six-fold improvement. And this is the power of a data warehouse. See, instead of just looking for single, obvious red flags, the analysts could now search through years of historical data to find really subtle, complex patterns. Things like multiple refunds all going to the same bank account, or a single address that suddenly pops up on dozens of returns. This let them build a much more accurate picture of what a fake return actually looks like.
And that accuracy? Well, it translated directly into dollars. In just one single filing season, they recovered an estimated $10 million. That's more than triple what they would have caught with the old system. And they did it all while hassling way fewer innocent taxpayers.
So what's the big takeaway here? What does this all mean for the future? Well, this story is way bigger than just one state's tax department. It's about a fundamental shift in how we find clues in a world that is just overflowing with data.
You see, the very same principles that caught those tax cheats are used by businesses everywhere. This is the engine that powers what we call business intelligence. It helps companies understand customer behavior, optimize their supply chains, and make smarter, data-driven decisions every single day.
In this technology, it's not standing still. It's constantly evolving. We're seeing the rise of things like data lakes, which are just these massive repositories designed to hold all kinds of messy, unstructured data, like social media posts or weblogs. Cloud computing is making these powerful tools more affordable and accessible than ever before. And new in-memory storage tech lets us do this analysis at lightning speeds. But the goal? It's always the same. Process more data more quickly to find those crucial hidden patterns.
Which, brings us to our final question. We are creating data at an absolutely explosive rate. So, will powerful tools like data warehouses make it easier to find the truth that's hidden inside all that noise? Or will the sheer volume of information actually make the truth harder to find than ever before? It's definitely something to think about.
Welcome back to the deep dive. We're constantly swimming in this massive ocean of information, just data noise everywhere. Our goal here is always to help you, our learner, filter that noise and find the real actionable knowledge within.
That's right. And today, we're really getting into the engine room, you could say, the foundations of how organizations actually make sense of it all.
Exactly. We are taking a deep dive today into the world of descriptive analytics. Specifically, we're talking business intelligence, BI, data warehousing, or DW, and visualization. These are the concepts, the tools, the structures that provide that informational bedrock.
They let us answer those absolutely critical questions: what happened, and maybe even more importantly sometimes, what is happening right now. It's about understanding the present and the past accurately.
And this isn't just theoretical. Our mission today is to give you a solid, comprehensive grasp of how data gets structured, how it moves around, and how it's finally presented visually so that people can actually make decisions based on evidence, not just gut feelings.
And the payoff, the immediate value proposition, can be huge. We're not just talking small tweaks here. Getting this right can fundamentally change how an organization operates.
Absolutely. Let's jump straight into a real-world example that just perfectly illustrates this. We're looking at the state of Maryland and how they tackle tax fraud. It's quite a stunning turnaround.
Oh, it really is. It's a classic case study. So for years, Maryland had this team, the Questionable Return Detection Team, or QRDT, and they were facing this mountain of potentially fraudulent tax returns, especially around identity theft.
Okay, so how were they trying to find the bad ones? What was the old way?
Well, it was pretty rudimentary, honestly. They were relying on, legacy software and really simple individual metrics. They'd look at a return, maybe check a specific ratio like income earned versus taxes withheld. If it tripped a flag based on these sort of simple rules.
It got flagged manually.
Exactly, manually flagged and suspended for review. Now, the scale here is important. Out of about 2.8 million tax returns filed each year, this system was flagging something like 110,000 of them.
Wow, 110,000. That sounds like they were being pretty thorough, maybe.
That's what you might think. But here's the kicker, the really shocking part. Of those 110,000 suspended returns, only about 10% were actually fraudulent. 10%.
Wait, seriously. So 90% of the returns they stopped were legitimate?
Precisely. Think about that. Somewhere between 90,000 and 100,000 people every single year were having their legitimate tax refunds held up, delayed, sometimes for months.
Oh, man. That's not just inefficient. That's creating a huge headache for ordinary taxpayers.
A massive headache. And a huge administrative burden for the state, too, reviewing all those legitimate returns. Their filtering mechanism was just too blunt, too reliant on simple rules that didn't capture the real complexity of fraud.
And I bet the fraudsters eventually figured out those simple rules.
You bet they did. The system was predictable. So Maryland realized they needed a major overhaul. Around 2010, they decided to invest heavily in a new approach, centered around building a proper enterprise data warehouse, an EDW.
Okay, so moving from simple rules to a data-driven strategy. How did the EDW change things?
Fundamentally, the first step was integrating and analyzing years of historical tax data, both the fraudulent returns and the legitimate ones. They built this rich database of characteristics.
So no more single red flags.
Right. Instead of relying on one or two simple metrics, they started using more advanced statistical methods, things like linear regressions. This allowed them to combine, dozens of different factors simultaneously.
Like what kind of factors?
Oh, things like historical filing patterns, where the return was filed from, variations in income year over year, the types of deductions claimed, relationships between preparers and filers, a whole multidimensional picture of what might make a return suspicious, rather than just one single trigger.
That sounds vastly more sophisticated.
Yeah.
So what happened? What were the results when they switched to this EDW-powered system?
The results were, frankly, dramatic. Almost immediately, the number of suspended returns, those false positives, plummeted. It dropped from that 110,000 number down to around 40,000 or 50,000 annually.
Wow, less than half the delays.
But that wasn't even the biggest win. The accuracy in identifying the actual fraudulent returns, that shot up from that dismal 10% all the way up to 65%.
65%, that's what, more than six-fold improvement?
A six-fold improvement in accuracy. They were catching more fraud while simultaneously hassling far fewer innocent taxpayers.
And the financial impact. Did they recover more money?
Significantly more. Under the old system, they were typically recovering about $3 million in fraudulent refunds during the filing season. With the new DW system, that jumped to $10 million almost right away. The ROI was immediate and massive.
That Maryland example just perfectly tees up our whole discussion, doesn't it?
Mm-hmm.
It shows the power of moving from noisy, transaction-level data and simple rules to this integrated analytical approach, reducing the noise, increasing the signal.
Exactly. And that power comes directly from having a properly designed data warehouse combined with effective business intelligence tools. It's the foundation for moving from gut feel to fact-based decisions.
Okay, so let's build that foundation for our listeners. Let's start with those core concepts. First up, business intelligence, or BI. Now, feels like that term has been around forever, but what does it really mean today?
Yeah, you're right. It's evolved. For a long time, BI was kind of a catch-all phrase for, almost any use of data in business. But now we tend to think of BI more specifically as the early stage of the analytics journey. It's primarily focused on descriptive analytics.
Descriptive analytics, that's the what happened and what is happening part.
Precisely. BI tools and activities are all about describing the current state or past performance of the business. It's about getting a clear picture.
And the tangible output of BI is usually reporting, right?
Reporting is the main product, yes. And that can take several forms. You've got your traditional static reports, the daily sales figures, the weekly inventory levels delivered on a fixed schedule.
The ones people often print out.
Or used to. Then you have ad hoc reporting. This is where a manager or an analyst can interact with the data, maybe through a graphical interface, to ask a specific one-off question that wasn't covered in the standard reports.
More interactive.
Much more. And increasingly, the most visible output of BI is the dynamic dashboard. These dashboards display key performance indicators, KPIs, giving you that constant, often near real-time view of how things are going. Like the dashboard in your car, but for the business.
Okay, so BI tells us what happened. But to do that reliably, it needs good data. And that's where the data warehouse, DW, comes in. Explain what makes a DW different from just, say, the database that runs the company's sales system.
That's a critical distinction. The purpose is completely different. A DW is a pool of data that is specifically structured and optimized to support decision-making. It's a repository, usually holding both current and historical data, designed for analysis, not for day-to-day operations.
Whereas the sales system database, that's an operational system.
Exactly. That's typically an online transaction processing, or OLTP, system. It's designed for speed and consistency in handling lots of small routine transactions, recording a sale, updating inventory, processing a payroll entry. It's not built for complex, wide-ranging analytical queries.
Got it. So Bill Inmon, often called the father of data warehousing, laid out 4 key characteristics that really define a true DW. Let's unpack those. The first one is subject-oriented. What does that mean?
Subject-oriented means the data isn't organized around the business processes, like order processing or invoicing. Instead, it's organized around the major subjects of the business, things like customers, products, sales, suppliers.
So the focus shifts from how the transaction happened to who or what was involved.
Precisely. In an OLTP system, you might query for order, #12345. In a DW, using the same underlying data, you'd ask, what were the total sales for product X to customers in the Northeast region last quarter? The structure supports answering those broader business questions.
Okay. Second characteristic, integrated. Sounds really important, especially given that data comes from all over the place.
It's arguably the most important for building trust. Integration means taking data from all those disparate sources, maybe an old mainframe system, a modern ERP, a CRM, external data feeds, and forcing it into a single consistent format within the warehouse.
So resolving conflicts, like one system uses CA for California and another uses California.
Exactly that. You have to resolve naming conflicts, differences in units of measure, kilograms versus pounds, inconsistent codes, different definitions for the same metric, like profit. The DW enforces the enterprise standard. If you don't do this integration step properly, different departments will get different answers to the same question, and nobody trusts the data. It's the key to that single version of the truth.
Makes sense. Third, time variant. This seems obvious, but why is it a defining feature?
Because the DW is fundamentally about historical analysis. It keeps data over long periods, months, years, even decades. Time itself becomes a key dimension in the data structure. You need that history to spot trends, understand seasonality, compare performance over time.
Unlike operational systems.
Right. OLTP systems often overwrite old data or only keep recent history to maintain performance for transactions. The DW is built to preserve that historical context. Time variance is essential for understanding change.
And the fourth characteristic, non-volatile. What does non-volatile mean in this context?
Non-volatile means that once data enters the warehouse, it doesn't change. It's read-only, essentially. If a transaction happens, it's recorded. If that transaction is later updated or deleted in the source operational system, the DW doesn't overwrite the old record. Instead, it typically records the change as new data, preserving the state of the data as it was at different points in time.
So you can't accidentally update historical records in the DW.
Correct. This stability is crucial. It means the DW isn't constantly being updated like an OLTP system, which makes it much easier to optimize for fast, complex read queries, exactly what you need for analysis. It ensures the historical record is stable and trustworthy.
Okay, so subject-oriented, integrated, time variant, and non-volatile. Those 4 pillars really separate the DW, designed for analysis, from the OLTP systems designed for transactions.
Absolutely. They serve completely different purposes, and trying to make one do the job of the other is usually a recipe for disaster. Running a huge analytical query on your live sales database could grind the whole business to a halt.
This clear distinction wasn't always there, though. Let's take a quick trip back in time. How did this whole concept of a separate data warehouse even emerge? What were things like in the 1970s?
The mainframe era. Data was centralized, yes, but it was often locked away in proprietary hierarchical databases. If a manager wanted some analysis, like quarterly sales trends, they couldn't just query it.
No SQL back then.
Not really, and certainly not easily accessible. You had to submit a formal request to the IT or data processing department. They'd let custom code, run batch jobs. You might get your report back in days, or more likely, weeks. The data existed, but it wasn't readily available for timely decisions.
Then came the 1980s, bringing PCs and departmental servers. Did that solve the problem?
Ironically, it created a new problem: fragmentation. Suddenly, every department could have its own little database on a PC or a mini computer. Marketing had its customer list, sales had its own, finance had another.
The islands of data.
Exactly. You ended up with multiple versions of the truth, inconsistent definitions, and it became almost impossible to get a reliable enterprise-wide view. People started trying to build distributed databases, but it was incredibly complex. This is also when specialized database companies like Paradata started appearing, focusing specifically on parallel processing for decision support, not just transactions.
And then the 1990s seems to be the real watershed moment.
Absolutely. That's when the modern DW really took shape. Bill Inmon published his seminal book, Building the Data Warehouse, in '93, laying out the core principles often associated with that top-down enterprise-first approach. Around the same time, Ralph Kimball started popularizing dimensional modeling techniques, focusing more on a bottom-up departmental approach.
We'll definitely get back to that Inmon versus Kimball debate, but first, let's clarify the different types of data repositories we often encounter within this world. We hear about data marts, operational data stores, enterprise data warehouses.
Right, it's not always just one monolithic thing. Let's start smallest. The Data Mart, DM. Think of a DM as a smaller, focused subset of a data warehouse, designed for the specific needs of a particular department or subject area, like a marketing data mart or a finance data mart.
Are they built from the main warehouse?
They can be. A dependent data mart gets its data from the central enterprise data warehouse, EDW. This ensures consistency, everyone's using the same integrated data. But you can also have independent data marts, which are sourced directly from operational systems or other places. They're often quicker and cheaper to build for a specific need, but you run a really high risk of inconsistent data definitions across different marts.
Okay, then there's the operational data store, ODS. Where does that fit in?
The ODS is kind of like the DW's short-term memory. It sits closer to the operational systems and stores very recent information. It's often integrated, like a DW, but it's updated much more frequently, maybe every few minutes or hours.
So it gives a more current view.
Exactly. It provides that near real-time snapshot of what's happening right now. It's often used as an interim staging area before data gets cleaned, transformed, and loaded into the more historical, stable EDW.
Which brings us to the big one. The Enterprise Data Warehouse, EDW.
That's the comprehensive integrated repository for the entire organization, or at least a very large part of it. The EDW pulls data from potentially dozens or hundreds of source systems, standardizes it all, and supports high-level cross-functional analysis for things like customer relationship management, CRM, supply chain management, SCM, business process management, BPM, the big picture stuff.
And underpinning all of this, the DMs, the ODS, the EDW, is something called metadata. Sounds important.
Critically important. Metadata is simply data about data. It's the descriptive information that explains what the data in the warehouse means.
Like a dictionary or an index.
Sort of, yeah.
Yeah.
It describes the structure of the data, table names, column names, data types, its meaning, business definitions, its origin, where did it come from, its lineage, what transformations were applied, when it was last refreshed. Without good metadata, the DW is just a huge pile of numbers that nobody can understand or trust. It's essential for usability and governance. We often talk about technical metadata, structural metadata, and business or semantic metadata.
Okay, that gives us a solid grasp of the core components. Now let's dive into the process, the plumbing, that actually moves the data and builds these structures.
Right. This is part 2, the plumbing process, integration, and architecture. It all starts with the data warehousing process framework. At a high level, you've got your data sources on one side.
The legacy systems, ERPs, OLTP databases, maybe external feeds like census data or social media.
Exactly. All that raw material. Then comes the absolutely crucial middle step, ETL. That stands for extraction, transformation, and load.
And you mentioned earlier, ETL often eats up something like 70% of the time and budget for a DW project. Why is it such a beast? It sounds simple. Get data, change it, put it somewhere else.
If only it were that simple. The complexity isn't really in the extraction, reading the data, or the load, writing it to the DW. The overwhelming majority of that effort, that 70%, is sunk into the transformation step.
Okay, break down transformation. What's actually happening there that takes so much work?
It's the heavy lifting of data cleanup and standardization. You're taking data from all those different sources, each with its own quirks, errors, and formats, and forcing it into that consistent, integrated state we talked about.
So dealing with the CA versus California problem, but on a massive scale.
Yes, but much more. You're cleaning the data, handling missing values, correcting known errors, removing duplicate records. You're conforming it, making sure product codes, customer IDs, dates, addresses all follow the same standard across the entire data set. Then you're applying business rules. This could be summarizing daily sales transactions into weekly totals, calculating derived metrics like profit margins, splitting or merging fields, applying data quality validation rules.
And those business rules might not even be formally documented anywhere.
Often they aren't. They might live inside old application code or just in the heads of longtime employees. Discovering, documenting, agreeing on, and then implementing these transformation rules in the ETL process is incredibly time-consuming and often involves a lot of negotiation between departments. That's where the 70% comes from. It's the intellectual property of how the business really runs, codified into data transformations.
That makes a lot more sense. And once the data is loaded into the DW or Data Marts,
then you need middleware tools that allow the end users, the analysts, the managers to actually access and query the data. Think of tools for OLAP, reporting, dashboards, data mining. They sit between the user and the warehouse.
Now, beyond the basic ETL flow, data integration itself is getting more complex, right?
Yeah.
With demands for real-time data, unstructured data, data from the cloud.
Absolutely. The landscape is constantly shifting. Modern data integration involves several key capabilities. There's data access, just being able to connect to and extract data from increasingly diverse sources. There's data federation, which is about creating a unified virtual view across multiple data stores without physically moving all the data, kind of like querying data where it lives. And there's change capture, which is crucial for efficiency, only capturing and processing the data that has changed in the source system since the last ETL run, rather than reloading everything every time.
Are there specific technologies that help with these challenges?
Yes, several supporting technologies play a role. We see things like EAI, Enterprise Application Integration, which focuses on integrating business processes across different applications. SOA, Service-Oriented Architecture, provides a way for applications to communicate through standardized services. And EII, Enterprise Information Integration, is often used for that real-time federated view we mentioned, frequently using standards like XML to integrate data virtually.
Okay, let's shift from the process to the structure itself, the DW architectures. This is where we see different design philosophies clash, particularly around how the central EDW relates to departmental data marts.
Right. We can start by thinking about the basic client-server setup. The simplest is a two-tier architecture. Here, the DSS engine, the software doing the analysis and reporting, runs on the same server hardware as the data warehouse database itself.
It's cheaper, I imagine.
More economical, yes, especially initially. But as the warehouse grows and the queries get more complex, having the database and the application competing for the same CPU, memory, and I/O resources can lead to significant performance bottlenecks.
So the alternative is?
The three-tier architecture. This introduces separation. Tier 1 is the client workstation running the BI tools. Tier 2 is the application server where the DSS BI engine runs its logic. And Tier 3 is the database server hosting the actual DW or DMs.
So dedicated resources for each function.
Exactly. It isolates the database workload from the application processing workload, leading to better performance, scalability, and manageability, especially for larger, more complex DW environments. It also makes it easier to support multiple specialized data marts fed from the central DW.
Now, within that tiered structure, there are those 5 main architectural models that represent different strategies for organizing the EDW and DMs. Let's run through them.
Okay, the 5 common alternatives. 1. Independent data marts. This is the simplest, often quickest to get started. Each department builds its own DM, pulling data directly from sources. But, as we said, it's chaos waiting to happen. Huge risk of inconsistent data, redundant ETL efforts, the lowest chance of long-term success.
Okay, slightly better.
2. Data Mart bus architecture, Kimball. You still build independent DMs, but they're linked by middleware, and crucially, they're designed to use shared conformed dimensions, like a common definition of customer or time. This promotes better consistency if managed well. It's often associated with Ralph Kimball's bottom-up approach.
Then the more centralized approaches.
3. Hub-and-spoke architecture. This is the classic Bill Inmon model. You build a centralized, integrated EDW first, the hub. Then dependent data marts, the spokes, are created from the EDW, tailored for specific departments. This ensures enterprise-wide consistency originating from the hub.
What's the downside there?
It can be complex and time-consuming to build the central EDW first. There's also potential data redundancy because data is copied from the EDW to the DMs, but it provides strong central control and consistency.
Option 4.
4. Centralized data warehouse. Forget the spokes. Just build one massive EDW that everyone in the organization uses directly for all their reporting and analysis needs.
Sounds simple conceptually, but maybe hard in practice.
Extremely hard. It offers the ultimate consistency and simplifies data management in theory, but it's typically the most expensive, takes the longest time to build, and can struggle to meet the diverse and specific needs of every single department from one monolithic structure.
And the last one.
5. Federated data warehouse. This isn't really a design pattern you'd choose from scratch. It's more of an approach to integrate existing disparate decision support systems after mergers or acquisitions. You try to create logical links and shared metadata across legacy DWs or DMs. It can be a pragmatic short-term solution, but it often inherits the inconsistencies of the underlying systems and has a relatively low success rate compared to the more planned architectures.
Okay, so these architectures directly lead into that famous Inmon versus Kimball development debate. It sounds like hub and spoke versus Data Mart bus, essentially, top-down versus bottom-up.
That's the core of it. Inmon's approach is top-down. The priority is enterprise-wide consistency. You invest heavily upfront to build the normalized integrated EDW first. Get the foundation perfect. Then you spin off dependent DMs as needed. It's rigorous, ensures consistency, but it's complex, slow to deliver initial value.
And Kimball's approach is bottom-up.
Right. Kimball argued, plan big, build small. Focus on delivering value quickly to individual departments. Build dimensional data marts first, addressing specific business needs. Enterprise consistency comes from ensuring these separate DMs all use shared, conformed dimensions and facts. It's generally faster, simpler to get started, delivers incremental value, but it requires strong governance and discipline to maintain that consistency across marts over time.
So for years, people argued passionately about which was better. Did any real-world evidence emerge to settle the debate?
Interestingly, yes. Several studies looked at the success rates of different architectures. The clearest finding was that the independent data marts approach consistently scored the lowest on pretty much every measure: data quality, business impact, user satisfaction. It just tends to lead to chaos.
Okay, so avoid that one if you can. What about the others? Did Inmon or Kimball win?
Actually, no clear winner emerged between the main integrated approaches. The studies found that the Data Mart bus, the hub and spoke, and the centralized DW architectures all had statistically similar success rates when implemented well.
So the takeaway for our listener is that the specific architecture might be less important than choosing an integrated approach and implementing it with discipline.
Exactly. The choice between, say, hub and spoke and Data Mart bus often comes down more to organizational factors: culture, budget, urgency, existing skills, rather than one being inherently technically superior to the other across the board. As long as you avoid the pitfalls of completely independent, uncoordinated marts, you have a good chance of success with a well-managed, integrated strategy.
All right, so we've got the data extracted, transformed, loaded, and we've chosen an architecture. Now we need to organize the data inside the warehouse or mart for fast analysis. This brings us to part 3, analysis and the dimensional model.
Right. Remember, OLTP systems are often highly normalized. Data is broken down into many small tables to avoid redundancy and ensure consistency during transactions. That's great for writing data, but terrible for complex analytical reads that need to join lots of tables. For a DW, we need the opposite. We need a structure optimized for querying.
And the most common structure for that is the star schema.
The star schema is the workhorse of dimensional modeling. It's simple, intuitive, and performs well for most BI queries. Visualize a star. At the very center, you have the fact table.
What goes in the fact table?
The fact table contains the core numerical measurements, the metrics, the things you want to analyze: sales amounts, quantities sold, costs, clicks, balances, counts. It's usually very large, potentially billions of rows. Crucially, it also contains foreign keys that link out to the surrounding dimension tables.
The points of the star.
Exactly. The dimension tables surround the central fact table. Each dimension table describes a specific aspect of the data, how you want to slice and dice those facts. You'll typically have dimensions for time, product, customer, location, salesperson, etc.
And what's special about these dimension tables compared to normalized tables in an OLTP system?
They are intentionally denormalized. This is key for performance. Instead of having separate tables for customer address, city, state, region, etc., a customer dimension table in a star schema might contain all of that descriptive information flattened into one wide table.
Why do that? Doesn't that create redundancy?
It does create some redundancy, but the benefit is massively improved query speed. By denormalizing, you drastically reduce the number of table joins needed to answer a typical analytical question. Instead of joining 10 small tables, you might only need to join the huge fact table to, say, 3 or 4 wide dimension tables. Fewer joins mean much, much faster queries, which is essential for interactive analysis.
Makes sense. You trade some storage space for speed. Now, there's a variation called the snowflake schema. How does that differ?
The snowflake schema takes the dimension tables from the star schema and starts to normalize them again. So, for example, your product dimension might be broken down into separate tables for product, product subcategory, and product category all linked together.
So it looks more like a snowflake than a simple star.
Right. The advantage is that it reduces that data redundancy in dimension tables, potentially saving storage space, especially if dimensions are very large. The disadvantage is that you reintroduce more joins into your queries, which can make them slower and more complex to write compared to the simple star schema. Star is generally preferred for its simplicity and speed unless dimension tables are truly enormous.
Okay, so we have the data dimensionally modeled in a star or snowflake schema. How do users actually analyze this data effectively? This is where online analytical processing, OLAP, comes in.
OLAP is really the technology and the set of techniques designed specifically for fast, interactive analysis of this multidimensional data stored in the DW. It's what allows users to ask those complex ad hoc questions and get answers back quickly.
What makes OLAP fast? Is it just the star schema?
The star schema helps, but the real magic of OLAP often lies in the concept of the OLAP cube. Now, this might be a physical structure or a logical view, but the idea is the same.
The cube, like a Rubik's Cube of data.
Kind of. Imagine your dimensions, time, product, geography, forming the axis of a cube. Each little cell inside that cube represents the intersection of specific values from those dimensions. For example, sales of product X in California in Q3. The key insight of OLAP is that many of these cell values, especially summaries and aggregations, can be pre-calculated and stored.
So when I ask for total sales in California for Q3, the answer is already computed.
Often, yes, or it can be computed very quickly from pre-aggregated components. Instead of the database having to scan billions of fact table rows and sum them up after you ask the question, like in a traditional relational query, the OLAP engine retrieves a pre-calculated result or quickly assembles it. This pre-aggregation is what gives OLAP its characteristic speed for slicing and dicing the data.
Let's talk about those OLAP operations. What does slice and dice actually mean in practice?
These are the common ways users interact with the OLAP cube. Slice. This is like taking a single slice out of the cube. You fix one dimension to a specific value. For example, slicing the sales cube by time, Q3 2024, shows you all products and regions just for that quarter. Dice. Similar to slice, but you're fixing values on multiple dimensions to zoom in on a very specific subcube, like sales for product X in California in Q3 2024.
Okay, slicing and dicing narrow things down. What about moving between levels of detail?
That's drill down and drill up. Drilling down means navigating from a summary level to a more detailed level. For instance, seeing total annual sales, then drilling down to see quarterly sales, then monthly, then daily. Drilling up is the opposite, aggregating from daily to monthly to quarterly to yearly.
And roll up.
Roll up usually refers to summarizing data along a dimension hierarchy. For example, rolling up sales data from individual stores to cities, then to states, then to regions. It's a form of aggregation based on the dimensional structure.
Finally, pivot.
Pivot, or sometimes called rotate, is about changing the orientation of the cube's dimensions on your screen or report. You might have products across the columns and time down the rows, then pivot to put time across the columns and products down the rows. It lets you look at the exact same data from a different perspective without rerunning the query.
So dimensional modeling, star
Yeah.
schema, provides the structure, and OLAP, cubes and slice dice operations, provides the fast analytical engine, all designed to get insights out of that warehouse.
Exactly. It's all about enabling that rapid exploration and understanding of business performance.
Which perfectly transitions us to the final layer. How do we actually present these insights to the humans who need to make decisions? This is part 4, the presentation layer, visualization, and dashboards.
Right. Because even the best analysis is useless if it's presented in a way that's confusing or overwhelming. Visualization is the key. And we define it broadly as the use of visual representations, charts, graphs, maps to explore, make sense of, and crucially, communicate information.
And visualization isn't some newfangled tech trend. People have been trying to visualize data for a long time.
Oh, absolutely. While you can find precursors going way back, Many credit William Playfair, working in the late 1700s and early 1800s, as the inventor of many of the modern chart types we still use today. He's credited with the first line charts and bar charts, maybe even the pie chart. He pioneered the idea of using length, height, and area to systematically represent numerical quantities.
But there's one graphic that often gets called out as perhaps the greatest ever made.
You must mean Charles Joseph Minard's map of Napoleon's Russian campaign from 1812. Edward Tufte, a giant in the field of data visualization, famously called it the best statistical graphic ever drawn.
What makes it so powerful? It looks complex, but it tells an immediate story.
Its genius lies in how it integrates multiple variables onto a single two-dimensional image. You have a thick tan band showing the path of Napoleon's massive army advancing into Russia. The width of that band directly represents the size of the army starting huge, around 422,000 men.
So you see the army shrinking as it moves east.
Exactly. You see the geographic path, the direction of movement. Then there's a thinner black band showing the path of the disastrous retreat. But here's the masterstroke. Minard links this black retreat line to a temperature scale plotted along the bottom of the graphic, showing the brutal winter temperatures during the retreat.
Wow. So you visually connect the dwindling width of the black line, the catastrophic loss of soldiers, directly with the plummeting temperatures and the geographic location.
Instantly, you see the devastating combined effect of attrition, distance, and cold. It tells a complex, multivariate story with incredible clarity and emotional impact. It's a timeless lesson that effective visualization is about conveying information density and telling a story, not just decorating numbers.
A high bar to aim for. So bringing that down to everyday business intelligence, choosing the right chart for the data is crucial. Let's quickly review the common types.
Okay, the basics. Line chart. Best for showing trends over time. Continuous data like sales per month, stock prices, temperature changes. Bar chart. Ideal for comparing quantities across different categories. Things like sales by region, website traffic by source, market share by competitor. Good for nominal or ordinal data.
The often misused pie chart.
Pie chart. Used only to show parts of a whole, like budget allocation percentages or survey response breakdown. And the golden rule, avoid it if you have more than, say, 4 or 5 slices. It becomes impossible to accurately compare the angles. A bar chart is usually better for comparisons.
Okay, scatter plot.
Scatter plot. Perfect for exploring the relationship or correlation between two numerical variables. Plotting advertising spend versus sales, for example. You're looking for patterns, trends, clusters, and especially outliers. You can sometimes add a third variable using dot size or color.
And geographic maps.
Geographic map, GIS. Essential whenever location is a key dimension in your data. Showing sales density by state, customer locations, store performance on a map. Often you'll overlay other chart types onto the map, like small pie charts in each state, showing product mix.
Now there's a distinction emerging between standard information visualization, which we often associate with BI, and visual analytics. What's the difference?
It's subtle but important. Information visualization, in the BI context, primarily focuses on that descriptive what happened or what is happening. Visual analytics goes further by integrating visualization techniques with predictive and even prescriptive analytics.
So moving beyond just looking backwards.
Yes. Visual analytics aims to answer why is it happening and what is likely to happen next. It involves highly interactive visual interfaces combined with underlying statistical models, forecasting algorithms, segmentation techniques. It allows users to visually explore complex patterns, test hypotheses, and interact with predictive models in real time. Think spotting anomalies in network traffic visually, or interactively segmenting customers based on multiple variables.
Whether it's simple BI reporting or advanced visual analytics. You mentioned earlier that it's really about storytelling with data. Why is the story aspect so important?
Because data alone is dry and often overwhelming. Facts and figures need context and narrative to be memorable and persuasive. A good data story provides the what, the key finding, but also the who is affected, the how did this happen, the why, what's the likely cause, and crucially, the so what. Why should the audience care? What should they do?
That makes the insight stick.
Exactly. Stories engage people emotionally and intellectually. Framing your analysis as a narrative helps decision-makers understand the implications, remember the key points, and feel more confident taking action based on the data.
And the primary vehicle for delivering these visual stories in BI today is the information dashboard.
The dashboard is king. It's that visual display, usually on a single screen, consolidating the most important information needed to achieve one or more objectives. designed for quick monitoring and providing pathways to drill down for more detail.
Stephen Few, another expert in this space, talks about dashboards having 3 layers of information. Can you explain those?
Yeah, Few's model is really useful. He suggests a good dashboard should cater to 3 levels. 1, monitoring. This is the top layer. High-level, graphical, often using visual cues like gauges or traffic lights, red, yellow, green. It shows the most critical KPIs at a glance, allowing users to quickly see if things are on track or if there's a problem. Very abstracted data. 2, analysis. If a KPI on the monitoring layer shows a problem, example sales are red, the user should be able to click or drill down to the second layer. Here, they find summarized dimensional data charts and tables that help them perform root cause analysis. Why are sales down? Is it a particular region, a specific product? This layer provides context. 3, management, the deepest layer. If the analysis layer pinpoints the specific issue, e.g. sales are down for product Y in the West region, this layer provides the detailed operational data needed to take action. Maybe a list of specific customers who stopped buying or individual low-performing stores. This is the action layer.
That's a great framework. Beyond the visual design, what are some best practices for ensuring dashboards are truly effective, focusing on the data itself?
Absolutely. The data underpins everything. First, benchmark your KPIs. Don't just show a number, show it in context. Compare it to targets, historical performance, or industry benchmarks so users know if it's good or bad.
Build trust in the numbers.
Yes, which leads to the second point. Wrap metrics with contextual metadata. Clearly display where the data came from, how fresh it is, last refresh time, maybe even the business definition. This preempts questions and builds confidence. Third, prioritize and rank alerts and exceptions. Don't just show everything, highlight what's most urgent, proactively push critical alerts to users rather than making them hunt for problems.
And
Finally, try to present information in those 3 levels Few described. The visual dashboard for monitoring, maybe linked to more detailed static reports for analysis, and potentially providing access to a self-service queued or tool for deep dive management actions. Cater to different user needs and analytical depths.
Excellent. That covers the presentation layer. Now let's move into our final section, part 5. Managing this whole infrastructure and looking at the future trends that are shaking things up.
Right. Running a data warehouse isn't a one-time project. It requires ongoing administration and security. The role responsible is the Data Warehouse Administrator, DWA.
What kind of skills does a DWA need? It sounds like more than just a standard database administrator.
It really is. The DWA needs a unique mix. On one hand, deep technical skills are essential, understanding database tuning for high performance, managing ETL processes, hardware configuration, networking, backup, and recovery. But just as importantly, they need solid business insight. They have to understand how the business uses the data to make decisions, so they can design the warehouse effectively, prioritize tasks, and communicate with business users. It's a blend of techie and business analyst.
And security must be a huge concern, holding all that integrated historical data.
Paramount, especially with regulations like HIPAA for healthcare data or Gramm-Leach-Bliley for financial data. Breaches can be catastrophic. Effective DW security usually focuses on 4 main areas: establishing clear corporate policies on data access and usage, implementing robust logical security like strong authentication, user roles, potentially data encryption, ensuring tight physical access control to the servers and data centers, and conducting regular internal control reviews and audits to verify compliance and identify vulnerabilities.
Okay, looking ahead now, the world of data is changing rapidly. Big data, the sheer volume, velocity, and variety is forcing the traditional DW model to evolve. What are the key future trends?
The biggest shift, arguably, is the rise of the data lake, DL. It emerged specifically to handle the challenges of big data that traditional DWs weren't initially designed for.
How is a data lake different from a data warehouse? Is it just a bigger warehouse?
No, it's fundamentally different in its philosophy and structure. A data lake is typically a large, low-cost storage repository, often using technologies like Hadoop HDFS or cloud storage like S3, designed to hold vast quantities of data in its native raw format.
Raw format, so structured data, unstructured text, images, logs, everything just gets dumped in.
Pretty much. Structured, semi-structured, unstructured, it all goes into the lake without necessarily having a predefined schema or structure applied up front. This is the key difference. The DW uses schema on write. You define the structure, like the star schema, before you write the data in. The data lake uses schema on read.
Schema on read, meaning?
Meaning you load the raw data first, and the structure, the schema, is only applied when someone needs to read and analyze that data for a specific purpose. This provides immense flexibility for handling diverse data types and for exploratory analysis, especially by data scientists.
So who uses which? Is the data lake replacing the data warehouse?
Generally, no. They are seen as complementary. The data warehouse remains ideal for business professionals and analysts who need reliable, consistent, structured data for standardized reporting and BI, using schema on write. The data lake is more suited for data scientists and advanced analysts doing exploration, discovery, and building predictive models on raw, diverse datasets, using schema on read. Many organizations now aim for a data lakehouse architecture that tries to combine the benefits of both.
Interesting. So the DL handles the raw exploration, the DW handles the polished reporting. What other trends are impacting DWs?
Speed and efficiency are huge drivers. One trend is real-time data warehousing, RDW, sometimes called the active data warehouse. This is about shrinking the latency, the delay between an event happening in the business and the data appearing in the warehouse down from days or hours to minutes or even seconds.
For that near real-time dashboard view.
Exactly, enabling truly operational BI. The challenge is that reducing latency significantly increases complexity and cost. Moving from daily updates to hourly is hard. Moving to minute-level updates is exponentially harder and more expensive.
Another efficiency trend is in-database processing. What's that about?
This tackles the problem of moving massive amounts of data out of the warehouse to a separate analytics server just to run complex algorithms, like data mining or machine learning models. With in-database processing, you push the analytics into the database environment itself. The algorithms run directly where the data resides.
Avoiding that data movement bottleneck.
Precisely. It dramatically improves performance for computationally intensive tasks like fraud detection, credit scoring, or complex simulations that need to process huge volumes of data quickly.
And the ultimate speed play seems to be in-memory storage technology.
Yes, this is about eliminating the slowest part of the equation: reading data from spinning hard disks. With in-memory databases or appliances, the entire data warehouse, or at least the most frequently accessed parts, are held permanently in the computer's main memory, the RAM.
Which is vastly faster than disk.
Orders of magnitude faster. We're talking microsecond access times. This enables incredibly fast query performance and complex calculations on the fly. The trade-off has historically been the high cost and volatility of RAM compared to disk, but as memory costs decrease and technologies improve, in-memory processing is becoming much more common for performance-critical DW and analytics workloads.
Okay, this has been a fantastic journey through the informational engine. We started with that Stark, Maryland example, 90,000 legitimate refunds delayed by an inefficient system.
And we trace the solution through the rigorous ETL process, the architectural debates of Inmon versus Kimball, shaping how data is organized.
The elegance and efficiency of the star schema and OLAP cubes for retrieval, and finally, how visualization and dashboards turn that data into compelling stories for decision makers.
We've seen how these integrated systems aim to maximize speed, consistency, and accuracy, moving from simple reporting to sophisticated analytics.
And throughout this evolution, the core promise of the data warehouse, its historical mandate, really, was to provide that single, reliable, cleansed, integrated version of the truth for the entire organization. That non-volatile, consistent view.
That was the bedrock principle. Schema on write guaranteed that consistency.
But now, as we've discussed, the future includes the complementary data lake. And the data lake, by design, holds massive volumes of raw, multi-format, often unvalidated data using schema on read. Data scientists increasingly work directly with this raw data for their modeling.
They might pull data from multiple sources within the lake, apply their own transformations, build predictive models, often bypassing the traditional DW's rigorous cleansing process to get insights faster, or from sources the DW doesn't include.
Which brings us to our final, provocative thought for you, our listener, to mull over. If critical business decisions driven by predictive models and AI are increasingly based on insights derived from this raw, potentially inconsistent, multi-format data presiding in the data lake, does the rise of the complementary data lake fundamentally redefine what the truth means in the enterprise? Is there still a single version, or are we moving towards multiple context-dependent truths?
Something to think about. The definition of truth in the data world might be getting a bit more fluid.
Definitely something to ponder. Thanks for diving deep with us today on the Informational Engine. We'll see you next time.